Hello everyone, welcome to 1045 Engineering. We are here with yet another video in our Grind 75, a Better Blind 75 coding series. So today we have reached our 73rd problem out of 75. It's a we are almost close to our final milestone here. So today's problem is on maximum profit in job scheduling. This is one of the most frequently asked interview questions for top product level companies or the FANG companies. So let's just quickly jump into the problem statement, understand it and start solving. Last time we have solved the basic calculator. I'll mark it checked. You can find this in the list. Let's start with maximum profit in job scheduling. Okay. We have n jobs where every job is scheduled to be done from start time I to end time I. Okay. Obtaining a profit of I. Okay. We are given the start and profit arrays. Return the maximum profit you can take such that there are no two jobs in the subset with overlapping time ranges. Okay. If you choose a job that ends at time x, you will be able to start another job that start at time x, or of course after x. Now if you see, we are given the example with the start time 1 2 3 3. So 1 2 3, we can see this job is starting at 1, this one is 2, this one is starting at 3, this one is starting at 3. End time is 3 4 5 6. First one is ending at 3, next one is ending at 4, third one is ending at 5, the last one is ending at 6, and the profit for each job is 50 10 40 70. Okay, I hope the problem statement is very clear to you guys. Again, this is not just one question. This question represents a lot of similar questions, and this is one of frequently asked approaches and the questions. Okay, so before I start, please take a minute and think of an approach that you will take to solve this problem. Ready? Okay. Now we need to notice few things. Okay, let's see what all can we derive from here. We can see when we can pick any job, right? Let's say I pick the first job. We got the profit 50. So I can pick any next job only after this job is done. So this job ends at 3, or let's consider it's starting at 1 p.m. ending at 3 p.m. I can pick up a job that starts at 3 p.m. What if I pick the third job that provides me profit of 40? So that will end at 5 p.m. But after 5 p.m. I cannot start any new job, right? So overall profit would be 50 plus 40, that would be 90. But the other case is, what if I pick this job as the overall profit? I get 50. Once this job ends, I pick up the fourth job, or we pick up the fourth job that provides a profit of 70. So overall profit would be 50 plus 70, 120. Right? So we can see that at each index we can actually use dynamic programming here. At each index we can see what was the biggest profit at that point. So let's say at the end of 3 the biggest profit found was 50. At the end of 4 the biggest profit could have been either I could have picked 10, or the initial profit at 3 was 50, so 50 is bigger. At 4 also the biggest profit is 50. At 5 we can find 40. We could have completed 40, and before completion of 40 was there a possibility to pick up another job? So if we start from the reverse order, it makes more sense, right? So we check that if at 5th index we would have picked up 40, then we'll reduce its start time, and from there we'll see we could have picked another job. So by index 4 the maximum profit was 50. For index 5 we'll see 40 plus 50, 90. We'll update the index. Now at index 6th we'll check that we could have picked this job, right, with the profit of 70, and before this job starts, was there any job that was ending before or at the start of this job that we could have picked up and completed? That was 50. 50 plus 70 is 120, which is bigger than 90. So 6th index will contain the answer 90. So of course we'll use dynamic programming to solve this solution. Now if end time is making more sense, maybe we should sort our array based on the end times, right? With these two things in mind, let's start with our solution. Okay, so what we are going to do is we are going to put up an array of jobs. We are going to sort them in descending order so that we know which job we can pick first that can end first, right? Again, one more thing is we'll keep a dynamic array to keep count of the profit, maximum profit at that index, and if there is a bigger profit available, we'll update the profit. Okay, so let's start. Okay, first let's get the int n is equal to start time dot length. Now all the indexes, all the arrays are same, so we'll have the same length. Now we'll create the array for the jobs, so we can say create an array of jobs to store start time, end time. Oops, let's remove this space. Start time, end time, and profits, right? So we can say int jobs is equal to new int n and 3. It's a 2D array because each subsequent internal array has the start time, end time, and profit for all the jobs, right? So we'll say for int I is equal to 0, I is less than n, I plus plus. We'll fill this array, right? So jobs of I is equal to new int, and we'll fill them with the start time of I, end time of I, and profit of I, right? Okay, now we will sort our jobs in the descending order, or not the descending order, based on their end times, ascending order but based on their end times. So sort, we can say sort the jobs based on end time. So arrays dot sort jobs, and we'll pass our comparator dot dot comparing. And what do we want to compare it on? We need to compare it on the end time, so we need to provide it comparing int a. We'll use the lambda expression, and based on the a of 1, that is the end time, right? Let's see, arrays dot sort jobs comparator comparing int. We have used it correctly. Okay, now we'll create our dynamic programming array, dp array, to store the maximum profit at each index. Okay, so we can say int dp is equal to new int of size n. Okay, and we'll initialize the first index with the first profit from the first job. So dp of 0 is equal to jobs of 0, and the end profit is at the third index, so 2, that is 0 1 2. I'll comment it, initialize with profit of the first job. Okay, now we can actually start our iteration process, where we iterate through our overall start time, end time, and the profit, means overall jobs. So iterate through jobs. Since we have the array also named as jobs, so I'll say provided jobs. Okay, so for int I is equal to 1, since we have already considered the 0 to provide it to the first index from 0th index on dp, so first job was already considered. Int I is equal to 1, I is less than n, I plus plus. Okay, now we are going to find out the current profit. Int current profit, let's say that is for second one. Okay, since you can see the end times are already sorted 3 4 5 6, so we can consider this exact example. First dp of 0 right now, let's write here, okay, in the comments. Dp looks something like this as of now. Okay, first profit that it would have received is from the first job, that is 50 at the 0th index. At the first 0, then 0, then 0. Overall there are 4 jobs, right? Now we'll check the current profit for the first job, that means the second job, that is this one. Starts at 2, ends at 4, profit is 10, this one. So current profit is equal to jobs of I and 2, right? Now we have to find one more thing. We have to find out if, as we discussed earlier, okay, please pay close attention. If we are picking this job, was there a possibility that we could have picked another job which was ending before the start time of this one, right? That's how we'll eventually reach the final solution. So let's create another method for this. We'll search it via binary search. So we can say binary search to find the latest. Okay, why the binary search? We have to find previous jobs. There can be many previous jobs. Let's say for the last case, or if it was a bigger array, there can be many previous jobs. We have to find the job that is closest to the start time of our current job, right? That's end time is closest to the start time of our current job. So we can say binary search to find the latest job that doesn't, and plus it shouldn't overlap, right? Doesn't overlap with the current job. Okay, so we can say private int binary search. What all do we need? We'll pass it from here only and then see. So we'll call binary, or not call binary search directly. We'll say int what should call previous compatible job index is equal to binary search jobs and the index I. Okay, so here we have to say int doubly brackets jobs and int current index. Okay, one is extra. Okay, we'll say int low would be 0, int high is going to be current index minus 1, current index minus 1. Okay, now normal binary search that we always use, right? While low is less than equal to high, we'll check for our conditions. Before that we need our mid. Int mid is equal to low plus high whole divided by 2. Whole divided by 2. Yeah, then we can say if jobs of mid and 1. What is 1? 1 is our end time. Okay, so if on the mid index the end time is less than equal to jobs current index start time, that is 0. If this happens, we'll check if it is possible that the next job is also ending before it. So if jobs mid, not mid, we'll check one index above it, mid plus 1, that is end time is less than equal to jobs of current index, okay, and 0, that is start time. If this happens, okay, that it is less than equal to, so we already know that it is less than equal to mid of 1, but we are also checking if it is less than equal to mid plus 1 of 1, right, to the next index also. If this happens, we can update our low as mid plus 1. Otherwise we can simply return our mid. But in case none of this is working, we can simply say else high is equal to mid minus 1. Okay, now after all of this, if we do not find it, we'll simply return return minus 1. Okay, so all that we are doing with this binary search is we are trying to find a valid index of a job that could have ended before we picked up our current job. In this case, our current job is one second job, that is profit equal to 10, represented by profit equal to 10. This job that starts at 2 ends at 4, right? Previously compatible any job would not be there for this job, so it will come out as minus 1 since we are returning minus 1. Now we'll calculate the maximum profit for the current index. Okay, so we'll say maximum profit for the current index. Current index. As we discussed, maximum profit at current index could be the current profit plus the previous profit if there was a possibility, or the maximum profit of one index back, from since we are storing the maximum profit at each stage in the dynamic programming array, DP array. So we can say dp of I will be equal to math dot max. We'll check for the last index, dp of I minus 1, or let's say current profit. So let's assume we are at the fourth last task, so current profit, that is 70, plus since before this there is a possibility, right, that we could have picked this first task before fourth task, we could have picked first task and finished it, right? So in that case, previous compatible job index would have resulted with the job index of 0, right? So we can say current profit, math.max of dp of I minus 1, or current profit plus, we'll check if what are we receiving in our previous compatible job index. Compatible, I created a very long variable, job index is equal to minus 1. If it is equal to minus 1, then simply 0. Oops, this is not 0, no, simply 0. Wait, did I add more than required? We have dp, we have this, okay, 0. Otherwise we'll check for that compatible index. The previous compatible index will return for the fourth job would be the 0th jobs index, that will be index 0. So we can say dp of previous compatible job index, right? Okay, let me expand this a little. Okay, right? And if after all of this, in the end we will have the solution that will be stored at the final index or the last index of the dynamic programming array. So we can say return dp of n minus 1. That's it. Okay, let me just run it once to make sure that we do not have any compilation issues. We do have. What is the issue? Where are we? We return arrays dot sort. We are sorting at jobs. Comparator dot comparing int. I know comparing int is method. Okay, arrays spellings are correct. Is dot jobs, that is correct. Comparator, comparator, comparator dot comparing, comparing. Spelling mistakes. I hate spelling mistakes, but what can we say, right? Okay, so it's working fine. Now let's go through this one more time. Okay, so we have our jobs. Okay, how we are trying, the crux of the solution is how we are trying to solve this problem is, let's look at it from the last end, that at index 6th this job is ending, the fourth job. This is first job, second job, third job, fourth job is ending at the last index. So I picked this job. Now the current profit or the profit that I'll be getting from this job will be 70. right? Let's note it as a current example. So current profit for the fourth job will be 70, right? Now when this job started, it started at index 3. I want to find out, was there a possibility that I could have picked up another job that ended before start of fourth job? So we searched through binary search. Now binary search in this case returned us that yes, job 0, you could have picked up job 0 that was starting at index 0 and ending at index 3. Okay, so we checked, we got the index for the 0th job, so it returned us 0. Okay, now we checked dp of I, that is for 6th index, would be math.max of dp of I minus 1. Let's ignore that for now. Or current profit, that is 70 plus previous compatible job index equal to minus 1. No, right? Otherwise we'll just save 0. Okay, like in this case, for this one, second job, we do not, first job will not have any previous compatible index, will have 0. For second job also will not have any previous compatible index. So for the fourth job, we got the previous compatible index as 0. Now we search in our dp array. If I expand it, dp array, the previous compatible job index, that dp of 0. What was dp of 0? Dp of 0 was the first profit, that was profit of 50. So 70 plus 50, that is the biggest. 70 plus 50 is 120. We update dp of I as 120. Okay, now again, just to provide a quick dry run, first we initialize the dp as 50, rest of the values are 0 0 0. Okay, we got the first profit from this. We iterated through the jobs, we went through the current profit. For the next one, the current profit was 10. Okay, we did a binary search to find a previous compatible job index. For this case, there was no previous compatible job index, it returned minus 1. We checked math.max dp of I minus 1. dp of I minus 1, we are at first index, so dp of 0 is 50. Or current profit, that is 10 plus previous compatible job index is equal to minus 1. Yes, so this is 0. 10 plus 0 is 0. Out of 50 and 10, which is bigger? 50. So this gets updated to 50. Next time, the index plus plus, we pick up this job, the third job. Now for this, current profit will be 40. We'll try to find a previous compatible job index. Yes, there was one job, first job, that was ending before this job was starting, so it will return us the index of that job, that is 0. Now we'll check math.max of dp of I minus 1, that is 50, or current profit 40 plus previous compatible job index is equal to minus 1. No, right? So we'll check for the dp of index 0, we'll have the 50. We have 50 as the previous at the 0th index, right? So 40 plus 50 is 90. So dp of I is 90. This one will become 90. Now similarly, we'll move forward. In the last one, we'll check that okay, current profit is 70, right? Previous compatible job index, we'll find yes, there was a previous job available, that will return 0. We'll check math.max or dp of I minus 1, that was 90, or current profit 70 plus previous compatible job index in the dp array, that is 0. So 70 plus 50, our overall profit would be 120 in the end, and then we'll return 120 here. I can say return result. Okay, let's submit with this. I hope this was clear. In case this was not clear, please go through the video again and understand this. Okay, and yes, okay, it beats only 32% of the users. I was actually hoping that, because this is there might be few more efficient approaches to this one. You can please take a look at them as well, and if you are aware of any of those, please let me know in the comment section. I could not find a better solution on this one. Okay, plus from the understanding perspective, this was the most approachable one. And yes, the overall time complexity will be O of n log n, that will be because of the binary search, and this one would be O of n, but O of n log n will supersede it, right? So overall time complexity will get O of n log n. For anything else, please let me know in the comment section, and in the end, please like, share and subscribe. Thank you.